What I was first programming was very simple things. So for instance, one of the ideas that I had that what to implement is the dice playing game. So where you have to guess the number of dice that somebody else has rolled, or you're trying to get certain combinations of dice and try to beat the others in the score that you get for them. And so I took the rules of the existing games and translated them into a computer program that would evaluate those rules and then provide the sequence of causal actions that are necessary to turn this into a game. And then, for instance, to automate the other players. So I could play against the other players. And then the game would at once be the one that evaluates the performance of the other players, but also produce the causal structure of the game. And by building toy problems like this, I got deeper intuitions about how programming actually works and how it translates your ideas of causal models, of causal reality, into code that is enacting these causal models. And in some sense, programming code is causal models. And the building blocks of programming code are the commands, the computer commands or the operators in which you express your programs. And what's interesting is that the programming language do not differ in what they can do. They only, because they all let the computer do exactly the same things. They differ in how they allow you to think about what the computer should do. So they provide different levels and kinds of abstractions to ultimately make the computer go through a sequence of steps that manipulate bits at the lowest level. And at the lowest level, there are automata in the CPU, and you can have different sets of automata that produce the same thing. And it's something that already was known to Wittgenstein, who already knew, as is, for instance, explained in the introduction that Russell made to the Tractatus, that you only need the NAND operator, the not AND operator, to build the entire logic. Right. And there are different ways to build the entire logic, but to get to this notion that later was known as Turing completeness, you can have many, many variants of such building blocks that allow you to eventually build anything that you want. So it's relatively simple to get such a set of building blocks. And this Turing universality was something that that Wittgenstein was already aware of, and Turing was his pupil. But Wittgenstein, I think, did not see it as significant enough to spell it out. But I think it's one of the big philosophical insights of the last century. The first philosophical insight of the last century that is really significant in my view is, one of the biggest ones, is Gödel's insight that the languages of mathematics that have stateless truths, that have stateless computation, are leading into contradictions. There are certain things that you can specify in these languages, but that cannot be implemented. And this is ultimately what Gödel's proof is about, that in these stateless languages there's always sets of statements that you can express, but they cannot be translated into any constructive enactment. And the solution, I think, to this is to discard these languages and go to languages where your semantics is identical to the implementation. And these are computational languages. And this is the first result, that basically the representational languages of mathematics are allowing too much. They are allowing to construct things that are leading into contradictions that cannot be implemented and so on. Versus the computational languages can do all the things that before worked in mathematics, but they can only do the stuff that can actually be implemented. For instance, can exist in a physical universe as we understand it. And the other one is this universality, that all these computational languages ultimately are the same language, that they can all express the same thing. And that's philosophically very significant because it allows us now to generalize the way in which we build models about reality and realize that all the models they are building, that we can possibly build, including all our mental representations, the echoes that we make of reality, the perceptions that we have, stuff that we can talk to, that we can refer to, are in this domain. And that's quite significant. So to answer your question from the beginning, the reason why I'm interested in computer science is because I believe that it provides a foundation, a representational foundation, ultimately also an epistemological foundation to make sense of reality. And it has left mainstream philosophy in a way in the dust, and mainstream philosophy is unaware of that. And as a result, it seems to me, as now an outsider to philosophy, that it's mostly dealing with problems that other philosophers have, but not in the same sense as Kant. It's not a provider of insights for the everyday working man, right? There was a time when philosophers were trying to produce insights that could be used outside of philosophy, and I don't see this very much in today's philosophy. Today's philosophy is mostly serving other philosophers.